Welcome to Frequency Domain Fluorescence Lifetime Imaging System Improvements and Applications, a webinar presented by PCO and hosted by Photonics Media. My name is Robin Riley, and I am the Photonics Media web editor. I would like to introduce Gerhard Holst, head of the Research and Science Department at PCO AG. Dr. Holst will be speaking today on the PCO film camera and the multiple enhancements that have been made to this camera since its introduction in 2014. If you have any technical issues during the webinar, please log out and log back in to rejoin. A recording of the webinar will be available on the Photonics Media website shortly after the presentation. We encourage you to ask questions throughout Dr. Holst's presentation. Just type your question in the question box to the right of your screen, and we will answer as many as possible at the close of the webinar. And with nothing further, I would like to introduce our speaker, Dr. Gerhard Holst. Welcome, Gerhard.
Thank you, Robin, for the nice introduction. Good morning, ladies and gentlemen, for this seminar about improvements and applications of our frequency domain fluorescence lifetime imaging system. A pretty long title for a relatively easy to use system, in my opinion. This slide provides an overview of what I would like to talk about in the next approximately 50 minutes. First of all, I would like to start with a short repetition of what frequency domain FLIM with a camera system is about. Then I want to explain how we improved the FLIM camera readout and the associated referencing. After that, I show and explain to you why we created our own laser light source for nanosecond FLIM measurements. Further, I explain how we use the phasor plot feedback and explain the way how we improve dark field or background correction. For the special case of a rapid frequency domain FLIM operation, I'd show how we suggest to do a proper symmetry correction, which is usually done by averaging with an additional inverse phase measurement. Finally, I want to show a variety of different applications to you to illustrate where the FD FLIM system can be used for. But let's start with the repetition of the camera-based frequency domain FLIM method. For this, I want to present you a short version of a tutorial that
By the development of a novel, fast, modulatable CMOS image sensor, the QM-FLIM2, the so-called frequency domain method became more attractive. In this frequency domain approach, the intensity of the excitation light is continuously modulated using sine or square waves. The modulation source is the camera, which provides modulation frequencies ranging from 5 kHz up to 40 MHz, as well as the signal for dark gating. Using a sinusoidal excitation waveform, the emission waveform is also a sinusoid with the same frequency. It is delayed in time and shows a decreased amplitude, a decreased constant component, and a decreased modulation depth. By comparison of the excitation and emission sinusoids, the time or phase shift can be determined. The phase angle, phi. Also, the excitation and emission amplitudes, A excitation and A emission, become clear. And the constant components, B excitation and B emission. These characteristic parameters can be determined by sampling and reconstructing the emission signal by a kind of half-wave integration measured at least 4 different phase angles. The first half-period integration is done at a phase angle of 0 degree, giving the image I1. Subsequently, the next half-period corresponds to a phase angle of 180 degree, resulting in image I3. If then the onset of the camera integration is shifted by 90 degree and the detection is repeated, the first integrated image I2 will correspond to a phase angle of 90 degree, while the fourth image I4 represents a phase angle of 270 degree. By repeating these integrations during a given exposure time, a sufficient amount of light can be captured to obtain a better signal. Finally, a sine curve is fitted into the measured values in the images I1 to I4 for each pixel. This sine curve provides the phase angle phi, the amplitude A emission, and the constant component B emission, which are used to determine the corresponding fluorescence lifetime values. These lifetime images extend the information obtained by common intensity images. The reconstruction of the emission signal by means of half-wave integration requires a fast modulatable image sensor. This is where the modulatable high-frequency sensor QM-FLIM2 comes into play. It was developed by CSEM and PCO from 2007 to 2012. In this unique image sensor, each of the 1008 times 1008 pixels has two charge collection areas, tap A and tap B. An externally applied two-level modulation signal controls whether the generated charge carriers pass through tap A or tap B. By modulating the excitation light and the image sensor at the same frequency, specific phase shifts can be measured in each pixel. At phase 0, tap A is active. All charge carriers are collected in charge bucket A. This is image I1. At phase 180, tap B is active, and all charge carriers go to charge bucket B, resulting in image I3. This kind of charge swing enables the simultaneous record of I1 and I3 in the same camera exposure, creating a double image. The image sensor modulation is shifted relative to the excitation light. Then, a measurement is performed at a phase angle of 90 degrees. The charge carriers collected in tap A create image I2. Tap B samples the information at a phase angle of 270 degrees, creating image I4. At a maximum modulation frequency of 40 MHz, minimum half-period integration intervals of 12.5 nanoseconds can be achieved.
Okay, Gerhard, we'll go back to your screen.
Thank you, Robin. So now I'm back in charge of the webinar. If you keep the tutorial in mind with a camera-based frequency domain fluorescence lifetime imaging system, we want to measure the emitted sinusoidal light signal to determine the relevant parameters which characterize the signal: the amplitude, A emission, the constant part, B emission, with which we can calculate the modulation index, and the phase angle phi. And this we do as described in the video by integrating the light signal of half of the period. Again, here is the schematic. With the QM-FLIM2 CMOS image sensor, that is relatively easy to do. Per pixel, the sensor has a light-sensitive area or volume where the charge carriers are generated, and each pixel has two readout tabs which are controlled by an external signal, which is the modulation signal. This two-half period integration is then repeated with a different phase angle offset to measure a different phase angle position. By this, four integration result values are generated, which are used to reconstruct the sinus signal. From that reconstruction, we get the values that we are looking for: the amplitude, A emission, constant part, B emission, and phase angle phi. Unfortunately, the symmetry of the tabs A and B is not perfect, and this imperfection can generate additional noise in the image. But in a normal lifetime measurement, this can be solved easily by repeating the measurement with an inverse phase angle, as shown in the next slide. With the additional measurement down here, the asymmetry is cancelled out by averaging of the corresponding phase angle values. But this comes at a cost. It reduces, unfortunately, the maximum frame rate by 50%. Here you see an overview of the technical specs of the camera system. The camera has a resolution of 1008 by 1008 pixels with a 5.6 micrometer pitch. It records 45 double images per second, which makes 90 images, but I prefer to call it 45 double images because it's at a rate of 45 images. The modulation frequency range out goes from 5 kilohertz for measuring, for example, microsecond lifetimes, down up to 40 megahertz to measure down to nanosecond lifetimes. It also can accept an external modulation frequency range from 500 kilohertz to 40 megahertz. The quantum efficiency of 39% is not overwhelming, but it's pretty good for a CMOS sensor. It's not exactly scientific CMOS, but for this purpose, it's the best we can achieve. It has a dynamic of 10-bit and a readout noise between 14 electrons and 18 electrons volt. The available exposure or shutter times are from 1 millisecond to 2 seconds. Above 2 seconds, the dark current induced noise is too large. It's cooled with a delta of 30 degrees centigrade. Therefore, we achieve a temperature of 5 degrees centigrade of the sensor, which is pretty good for a lot of types of different applications. The power consumption assumes to be 60 watt. If we add to this camera system a proper modulatable light source for excitation, we can easily describe the structure or experimental setup of a frequency domain film system, which is shown in the next slide. Let's take the example of a microscope-based film measurement. We have the PCO film camera, which sends out a modulation signal and a so-called dark gate signal, which switches off the excitation light during readout of the images. Both signals are fed to an appropriate light source, which can use and handle the signals. The light then is coupled into an epifluorescence light input of an inverted microscope, for example, here with a liquid light guide. At the stage of the microscope, the modulated excitation light generates the fluorescence, which is imaged to the camera. The raw images with the integration results are transferred to the controlling computer with its software, which handles the camera control, the image processing, and storage. In this example, the software is the Nikon microscope software and NIS elements. One of the most prominent questions usually is, what is the right frequency for the fluorescence lifetimes we want to measure? You can derive this from theory, an equation for a lifetime range, which ends up in the following. Don't worry about all these mathematics. This is safe. But at the end, we have this nice equation that shows up here again. So the modulation frequency is calculated by 1 divided by 2 times pi and the square root out of the range of lifetimes. And if you only know a single lifetime, then it's even easier. It's just 1 divided by 2 times pi and the lifetime. So that's a good start for modulation frequency. Further, you need to do a reference measurement to figure out what the offset of your optical system is, because when you switch on, you usually don't know where the zero position is of your signal. And second, if you are going for nanosecond measurements, you have to be aware of that light travels in 1 nanosecond 30 centimeters. So every 30 centimeter distance in your optical setup will create an additional chance to figure out where the zero position of your optical system is. You can take any fluorophore where you know the specific lifetime. And this lifetime has to be in the range of the lifetimes you're going to measure in, or it has to be shorter. It's not working if this lifetime is a lot longer. So in general, any sample that you know and has similar spectral characteristics like the application will do. We are using, for example, these fluorescence references from Stana Scientific in England because it's simply comfortable to use them. They provide these small black slides with a plastic window where the fluorophore is dissolved, and We did with a different measuring system, a TC-SPC system. We did the lifetime measurements, and as you see here, the distribution of lifetimes is pretty good, so we assume apparent effective lifetime for the different samples that are described here. And they are simply used at the beginning of each series of measurements, so that's quite handy. Now I would like to explain to you how we improved the referencing by itself. The colored dots show the measuring results of modulation index and phase angle at 30 megahertz of our reference fluorophore, which had a lifetime of 3.7 nanosecond at various fluorescence intensities. The results could be expected as a flat line parallel to the x-axis, but unfortunately they are not. Fortunately, it's possible to measure that behavior and calculate correction coefficients, which can be used for correction. The curves through the data points show the result of the fitting process. The orange area, which states that some pixels start to saturate, should illustrate to you that we could never achieve 100% signal since we are integrating on a sinus signal. So the maximum signal without saturation of pixels that we could get is about 63% of the signal. Just to remind you to that. With a proper correction, we achieve the results that are shown in these two graphs right-hand side. They show the corrected results of the same reference measured at different intensities and different modulation frequencies. So up there are the modulation index based reference lifetimes, and down here are the phase angle based lifetimes. And by the standard deviations, you can see at the different intensities the precision we can achieve with such a measurement. So precision is plus minus 100 to 200 picoseconds in general. Some years ago, we started with a nice but unfortunately a bit complicated optical setup of a laser light source, despeckling unit, and a universal optical in-coupling for all microscopes. With some additional investigations, we were able to replace the system by an easier and fortunately more cost-effective one. And I would like to explain how we proved that. So here you see the original film measurement with a laser coupled with a monomode fiber into the despeckling unit and the optical imaging optics connected to the microscope. So when the despeckler was switched on, you got this fluorescence intensity image of these hex cells, which were expressing a Fred pair of indicators. If the despeckling was switched off, usually the interference patterns caused by a coherent laser light source are visible. You see this here. Now, if the optical setup with the despeckler and the monomode fiber is replaced simply by a liquid light guide, we get similar results like the despeckling on, with a much easier and simpler solution. But this is only intensity. So is the same result true for the lifetime measurements? Again, in this display, you see the color-coded distribution of phase angle-based lifetimes for the case of the despeckler switched on and despeckler switched off. Even in the phase angle, you see the influence of the speckles because they are not time-wise not stable. They are fluctuating. If I repeat the same measurement with the liquid light guide connection, you get this result, which is pretty much the same like the despeckler being on. Instead of showing a similar result for the modulation index-based lifetime, we can have a look at the corresponding phasor plot, where both values of each pixel, the modulation index and the phase angle, are used to create a vector in a Nyquist plot, which is in fluorescence applications usually called a phasor plot. Same measurement, different display of the same results, now with a phasor plot, and you can spot out the differences with D-spector off and on. And again, the liquid light guide gives the same result like D-spector on. Therefore, we decided to generate our own excitation light source to create a complete film system, which is shown here. This is the PCO film laser, which can be received either with a 3mm liquid light guide connector for wide field epifluorescence illumination, or in case a spinning disk system or a turf system should be used with a Kineflex adapter to couple in the same laser light into a monomode fiber. It's also fortunately possible to exchange the adapters afterwards. The laser has all trigger inputs and gate inputs, and it is equipped with all relevant safety shutters and features. The following schemes show how it can be connected to the PCO film camera system with its different operational modes. For single images, when the excitation light should stay on when the camera is not recording for scanning the samples with your eyes through the oculus, the modulation signal of the camera is fed to the digital input of the laser. And the dark gate signal is connected to the laser enable. In case you want to do a time-lapse measurement or you don't like the laser to be on while the camera is not recording, you might want to use the breakout cable, which is provided with the camera, and connect the exposure out to the laser enable. With this setup, the light only is on if the camera is recording or in preview or fine state. This in turn means if you want to investigate the sample with your eyes behind the oculus, you will have to set the camera in preview mode to switch on the light, and you will have to live with a flickering excitation light because the camera will always switch off the light for image readout. We use for that purpose the easy-to-use control software of the OEM manufacturer of our light source to adjust all parameters. Beside the standard settings, for the connection to a PCO film camera, the software mostly is used to adjust the light output power. Once it's set, it doesn't need to be touched. Datasheets and manuals for the PCO film laser, the adjustment of the Kineflex adapter, and how to do measurements with the NIS element software with the PCO film module are available. The next slide with its movie shows how the phasor plot feedback is used when you have done a reference measurement. Here you see the situation of a measurement of some hex cells that were expressing a fret pair of dyes. In the phasor plot window, you see the result of these hex cell thread measurement. From the intensity image, it's obvious that a large area in the image doesn't contain information. You see here the black spots between the cells. Nevertheless, the software tries to determine phase angular modulation index for values for these positions. The difference is that the intensity values of the pixels at positions between the cells are relatively small. Therefore, in the phasor plot window, you can change a level called minimum intensity to suppress the display of any pixels, and this is the start of the movie then. By changing this level, you can suppress the display of these pixels. They're not removed, but simply not displayed. And you see that also the noise color informations in the result images are removed, and the three distinct areas in the phasor plot are appearing. If you activate the intensity image, you can then play around with the lookup table to get a proper adjustment of the brightness. And then if highlight is activated, you can use the phasor plot with these ellipse or circles, which are used as a probe, because the phasor plot information is related to the pixels in the original images. So now every pixel within that green circle is painted green, if there is any. And so this is a long lifetime cell with a lifetime above 2 nanoseconds, because the parameter on the unity circle of the phasor plot is the lifetime. The red circle can be used to indicate where the short or the medium type of lifetimes are. And if you keep in mind that short lifetime with a FRET experiment means a high FRET efficiency, while a long lifetime means either a low FRET efficiency or no FRET, this gives you some information about which cells in your image show FRET and how much. You can switch that off and highlight again, and you get the same information if you have a look to the phase lifetime image, which is color-coded in the range of, I think this is now 500 picosecond up to 3.5 nanosecond. And now with pointing the cursor on the image, you can read out below the image the value of the nanosecond lifetime. And you see it is exactly the same like the phasor feedback. It's simply a different way of looking at it. What you can do further to get an information about the structure that is behind these lifetime values, you can switch on the intensity modulation display. Then the fluorescence intensity is used to weight the brightness of the color of the false color coding of these lifetimes. So there are different possibilities of getting the information of your cell experiment out. If I remove or put the level down, then again, more maybe noisy signals are popping up in the images. It's only to mention that if you don't use that level, then you have all the noise in the phasor plot and all the noise present in the image. By using that level, the more relevant distribution of lifetimes is popping up and becoming clearer in the phasor plot. For the handling of the offset and background value, first we used a constant value for the offset and the dark current, which was subtracted from the raw images before all image processing started. But with that, we always had a slight longitudinal extension of the modulation index values in the phasor plot, which all seem to have the same phase angle. We figured out by a lot of test measurements that all tabs have a slightly different offset. Therefore, we developed a proper procedure to measure the dark field or background, which has been integrated into the PCO FLIM module of the NIS Element software. Here you see the phasor plot where we simply subtracted a constant offset value, and this distribution of modulation index values reflects this artificial or longitudinal extension. With the pixel and tab-wise subtraction of the background value, we got an improvement in that. In the corresponding phase angle-based lifetime images, we don't see a difference, clearly because all these even smaller modulation index values have the same phase angle. But in the corresponding modulation index-based lifetime distributions, you see an improvement. So this has been integrated, and it's camera related, or better to say image sensor related, and it only has to be done once in half a year maybe. In case your application requires the highest possible frame rate, but you don't need the lifetime value as such, but a signal that corresponds to the lifetime, the rapid frequency domain FLIM approach can be quite helpful. Rapid FLIM techniques, which exist for both time and frequency domain, they are based usually on a two integral measurement in time domain, one after the other, and in frequency domain, two integrals simultaneously. These integrals are processed by either calculating a ratio or a normalized difference. The corresponding result would change corresponding to a lifetime change, but it cannot be converted to a real lifetime value because information is missing. If you remember the asymmetry correction from the beginning of the webinar, which has been solved with an additional inverse phase measurement, it's clear that this type of correction is contrary to the fastest possible frame rate. Therefore, we figured out a correction by measuring continuous light illumination of the two tabs A and B and a new fit function to describe the behavior of the tabs. These two graphs show the differences between tab and A and B of selected pixels before and after correction by using this empirically determined fit function, which can be used afterwards. And these two images show the improvement that we achieved, and they show the normalized difference. In the left images, it looks a lot more noisy because this was before the correction, and the same values after correction resemble much more the reality that has been measured. At the end of the webinar, I would like to show you a blend of different frequency domain FLIM applications, if my audio connection will be stable, hopefully. At the beginning, just a few photos of different experimental setups which range from microscopes to macro lens applications. So everything is possible in that perspective. Let's start with a standard FLIM application. This was a mouse kidney sample stained with Alexa 488, and the recording was done with a 20x air objective. This image shows the fluorescence intensity. This is the phase angle based lifetime distribution, and this is the same information with the intensity weight. It was recorded with an inverted Nikon microscope. This in turn is a FRET application. These were hex cells with CFP-YFP FRET pair that we have thankfully received from Professor Wouters and Dr. Bund in Göttingen. This is again the fluorescence intensity, and this lifetime distribution shows that these blue cells show FRET while the green ones do not show FRET. Again with an intensity weight. Another FRET application was done with a confocal spinning disk microscope, a Yokogawa CSU W1 at the University of Luxembourg, with BHK cells with GFP HRAS and M-Cherry HRAS FRET pair with a 60x oil objective. This is the intensity. It was a quite weak signal because unfortunately the optical output of the spinning disk system was not optimum for the FLIM camera because it expected a much larger sensor. Therefore, a lot of light was simply wasted. Nevertheless, we could do this measurement, and here you see the lifetime distribution and again the intensity weighted version of it. A different approach was with a TURF microscope. This was a Leica microscope. We were able to measure proper images down to 110 nanometer penetration. Below that, the signal was too weak. And this was tubulin GFP. Just a control experiment, so there wasn't any FRET to be expected. A different field of applications could be the endogenous fluorescence, so all the natural fluorophores that are within tissues or tissue samples. In this case, I think it was a human tissue sample. You see the autofluorescence and the lifetime distribution, and you could connect this to the structure of the sample. Maybe an interesting technical application is the separation or differentiation of microplastic. This was just an occasional setup. We received a lab air filter with microplastic particles. This was recorded with a 20x objective. This is the fluorescence intensity of this filter paper plus particles. This is the lifetime distribution. And here you see the phasor plot as well, and you see a broad range of different lifetimes. And together with the University of Rosenheim, we performed a lot more measurements of single different plastics, ranging from PVC to PET to PP whatsoever, and they all show a very much different lifetime. And therefore, these guys there at the university think it could be used for early detection of microplastic in water or in food. Could be a very interesting application, in my opinion. This shows a publication that has been done, a comparison of an old time domain film system versus the new frequency domain-based camera system. And this is about the measurement of oxygen in marine environment. Here you see after exposure of these plants, where you see the oxygen distribution about their roots, after 12-hour light, you see they are producing oxygen, and in the dark they are more or less consuming. And the upper two images were obtained with the old system, while the lower two images with the new system, you see it has a better spatial resolution, and that's also a better resolution in terms of signal. So it was a very nice application. A different application are other optical chemical sensors like pH sensors. This was an application at the Technical University of Graz. Even in the intensity, you could see a difference, but as well in the lifetime, these special pH indicators show a different lifetime. And you could see this in the phasor plot as well. And you could use these measurements of these planar optodes as well to read out profiles and calculate exchange processes. This was done by courtesy of Professor Thorsten Meyer, Professor Sergei Berisov, and Dr. Brigitte Ungerberg from the Analytical Chemistry at the Technical University in Graz, Austria. A different application with a similar pH optode was the measurement of the pH value on concrete, which can give information about the health status of the concrete. You see the measurement, the in phase angle distribution, phase angle based lifetime distribution, and the intensity value. Another application comes from Taipei in Taiwan, where they measured the oxygen gradients within microfluidic devices. This was also done. Very nice results. As the range of the modulation frequency is quite large, you can also do phosphorescence. In this case, the measurement of interest was the measurement of 5-ALA, which is injected before brain tumor surgery. And usually it's done in a way that the 5-ALA is accumulated in the tumor, and it's used as information for the surgeon how much part of the tissue has to cut off. Unfortunately, the intensity is not so precise as an information for the layout of the tumor. And these researchers have figured out that the lifetime gives much more precise boundary information. And you might imagine that in a brain surgery, it's very critical to cut off everything that is associated with cancer, but not cut too much, because this will create damage to the patient. These researchers are ongoing with the this application of the FLIM camera, and it will be interesting what they can figure out in the future. A more technical application is pressure-sensitive paint measurement, which basically is a optical chemical oxygen measurement, but on a, let's say, technical scale. And there people used the camera, evaluated it, and compared and created results in wind tunnel, where they do measure the oxygen partial pressure on the surface of models that are exposed to a higher airflow in the wind tunnel. This is a first rapid frequency domain FLIM application with nano-optodes. The calculation or evaluation of the signals is quite easy, so it's just a normalized difference. Although this was a slow application, so it's not really typical for rapid FLIM. It gives some information for the use about rapid FD FLIM measurement, which is, as an example, not a typical rapid measurement, because you by the time it takes, you see that it's not really fast. On the other hand, you see the diffusion of oxygen into that system. So the more greenish and the more brighter the pixels become, these nano-optodes show that there is more oxygen present over time. What I would like to show with that in the next slide, I'll start a movie. You see now on the right-hand side the fluorescence intensity, and you see the brownish movement of the particles within the water column vertical-wise. But you don't see this in the rapid FLIM readout, because this goes with the lifetime, and the lifetime is the indicator of the oxygen concentration, which means that although these particles are moving vertically, there's no vertical change of oxygen. Only in these small patches above or near to the water level, there you see oxygen moves, and this corresponds to the movement in the intensity as well. But the vertical movement seen here is not reflected by the lifetime measurement. If you would now read this out with a time domain rapid lifetime measurement, you will have artifacts, because you will record one after the other image, and therefore all the pixel informations are not at the same spot. With the rapid frequency domain FLIM, due to the modulation of the charge swing, we are virtually recording at the same time, so you don't get these motion artifacts. This is just for your information, and you can review this afterwards when the presentation is online. I wouldn't go through all these publications, but it's just a collection of publications that happen to be done with the PCO FLIM, and for sure there will be more. So thank you for all of you who showed the patience and attended through all the webinar. I'm sorry for the interruptions. And thank you for your interest in frequency domain FLIM. I'm finished so far with my presentation and open to answer questions. In case you later have more questions, please feel free and send me an email, and I'll try to answer them.
Thank you very, very much, Gerhard. That was a great presentation, and I know that you have some challenges there with your connection. So we'll begin with a question that came in, and it's a rather lengthy question, so if I need to repeat it, please let me know. Could the measurements of oxygen, pH, carbon dioxide, and temperature sensing be used to link ultraviolet fluorescence and fluorescence lifetimes to the nutrient-dependent, pheromone-controlled weekend resurrection of the bacterial flagellum in capital P period fluorescence via biophysically constrained viral latency?
That's certainly a very interesting question, but I think I'm the wrong guy to answer. If you're able to measure these parameters and do the proper connections of your results, that might be possible, but I'm not a biologist. I'm sorry. I think there are quite a lot of different optical chemical sensors out there, so it might be possible to measure all of that, not at the same time, but in similar environments with similar samples. But I don't have enough knowledge to answer, I mean, the biological associated conclusion of the question. So I'm sorry.
That's all right. We'll go to the next question here. And this question regards what is the suitability of using wide field fluorescence in 3D tissue imaging? And then he has brain in parentheses. So imaging of brain tissue, I think.
Well, naturally, I mean, I think I've shown one of the publications that has been done with a light sheet microscope. So you can use the film camera as well to do light sheet, and therefore to get tomographic informations. Or you use a confocal spinning disk. I mean, we've shown that you get good results with that too. Therefore, in that case, it's not a wide field illumination, but illumination of a plane in a wide field setup, or illumination of a confocal setup. So if I understand it right, yes, you can use film measurements with tomographic setups.
Okay, thank you. Regarding spectral resolution, can we see the decays of different wavelengths of light with time? And he also asked time constant sensitivity.
Sure, but maybe not at the same time, because if you're measuring at one frequency, you assume only one lifetime. If you want to get more information, then you will need to repeat the experiment at a different modulation frequency. The rest is optical. So whatever you select in terms of spectral emission is possible. So it doesn't matter whether the emission is in the blue, in the green, or in the red. The only limitation is the signal to noise ratio. So if there isn't enough signal, it's difficult. So if you have very weak samples, or if you want to use very narrow bandwidth of a bandpass filter for the emission, it might be a problem.
Okay, thank you. Do you plan any modulator laser combiners in the future?
Can be done. We've talked to our manufacturer, so they sell combiners. And we've already used one occasion to use them with our modulation. So in principle, it's done. It's not yet on the website. It depends a little bit on request.
Oh,
Technically, it's possible.
thank you. Can FLIM be used to view indium tin oxide coatings?
Unfortunately, I have no idea of the signal and the lifetime of these coatings. Principally, I would say yes. If the signal is large enough, it can be used. But unfortunately, I have no experience for that application.
Are single frequencies or multiple, and in parentheses they have parallel, comma, harmonic. Are single frequencies or multiple frequencies employed for imaging? Is either mode selectable?
At the moment, with the software that we have, we only support single frequency applications. In principle, it's possible, but then the bracketing and correction becomes a bit more complex. It's not yet offered as a feature. In principle, it's possible.
Thank you. Once the system is configured, could it be used for remote sensing?
If you can remotely control the controlling computer, I don't see any reason why it could not. Depends on the environmental conditions. I mean, for example, if you put the system in the sunshine of a desert, no. I mean, if the environmental conditions are okay, I don't see any reason why it could not be remotely operated. Maybe it turns down to more explain what the person understands with remote control. Because if there is a possibility of remote control of the computer, I don't see a problem.
Okay, thank you. I have a pulsed laser. Can I use it with your FLIM system?
Yes and no. Usually the pulse lasers have short pulses at a certain repetition rate, and you don't get enough light into your applications. So therefore, the pulse lasers are used for different type of time domain applications. You get more light if you use a modulatable laser. And you have both options of using the sinusoidal or the square wave modulations. Therefore, I wouldn't use a pulse laser, but I would not say no that it cannot be used.
Okay, thank you. Next question. I am interested in application of FLIM in photosynthesis and plant stress research. Are there advantages? Could it be used for that?
As far as I know, it can be used. The only limitation is that with the camera system and the conditions, it will be difficult to use it under bright light conditions. So the camera expects it to be dark around the measurement. Otherwise, the 10-bit dynamic might not be enough, because that's in general a problem that we face if people ask for lock-in applications. It is a lock-in camera, but many of these applications tend to be a small signal on a high background, and there the 10-bit might not be enough.
Okay, thank you. Is improved performance desired? We are interested in adding adaptive optics to increase resolution and contrast.
In my opinion, improved performance is always desired, so yes.
Okay. Next question here. I am interested in knowing FLIM's application in environmental protection.
Depends on what you're going to measure. I mean, if the lifetime of autofluorescence of a plant, or if you're looking for microplastic or whatsoever, I mean, if there's any value of this parameter fluorescence lifetime, and if it can be detected under the conditions you are going for, yes.
Okay, thank you. Do I need a Nikon microscope to use your FLIM system?
No. We use a Nikon microscope because we have a good relationship, and I have one in my lab. And certainly at the moment you will have to use the Nikon software, but just for controlling the camera and do the image processing, because that's the only software that we use so far to control our camera. But in principle, the SDK, and if you want to do it on your own, that's always possible, but it will take some time to implement all the corrections and all the things that we have done so far. But it's not necessary to use a Nikon microscope.
Okay, thank you very much, Gerhard. I'm going to have one more question here, and then close the webinar. And meanwhile, attendees, if you have any questions, do please add them into the question box, and I will be sure that Gerhard receives your question as well as your contact information. So our last question here will be, can your frequency domain FLIM system be used with a Yokogawa spinning disk system?
Sure. But attention has to be paid on the optical output. So if the Yokogawa system is made for, let's say, an EMCCD camera with these large sensors, it will give you a hard time to get enough signal. I've made a lot nicer measurements with an older system from Yokogawa, the CSU-10, which just illuminates a small area. I mean, the principle is the optical output. If you illuminate a larger area and you cannot use it, you're wasting light. So for that purpose, you will have to talk to Yokogawa to get a better focusing of the light on a smaller area. And then it's possible, yes.
Okay, thank you very much. And at this time, I'm going to close the webinar. A recording of the webinar will be available shortly. Everybody will receive a link to the recording tomorrow in a follow-up note. And I would like to remind everybody that if you do have a question, please contact Gerhard directly, or there's still a few seconds to add it in to the question box. I would like to thank PCO. I would like to thank our presenter, Dr. Gerhard Holtz, and all of you for participating in Frequency Domain Fluorescent Lifetime Imaging System Improvements and Applications. Today's webinar presented by PCO and hosted by Photonics Media.
Thanks as well from my side.
Thanks, Gerhard.